Today we're going to revisit one of my favorite integrals. Now, I've already solved this integral on the channel using integration by parts and some interesting substitutions that made use of symmetry, but the solution development using Feynman's trick is just way too cool. And it involves complex numbers. I believe I've said enough, and we should begin the solution development. We'll start off by defining the integral function I of some parameter alpha, and we'll define that as the integral from 0 to pi by 2 of inverse tangent cosine squared x times alpha divided by cosine squared x integration with respect to x. So that means we're interested, that is the target integral is I of alpha equal to 2. And we also have some useful information here that if we plug in alpha equal to 0, we get integral from 0 to pi by 2 of inverse tangent of 0 divided by cosine squared x dx. And we know that the inverse tangent of 0 is, well, 0, so the entire thing collapses. So we know that I of 0 is 0, and we're interested in I of 2. Okay, so that means we have an excellent plan in place. So we differentiate the integral function with respect to alpha, and switch up the order of the integration and differentiation operators. That gives me the integral from 0 to pi by 2 of now the partial derivative with respect to alpha because of the Leibniz rule of inverse tangent alpha cosine square x divided by cosine square x dx. And the squared cosine term is going to be treated as a constant because we're differentiating partially with respect to alpha. So we have 1 by cosine squared x, and we have to differentiate the inverse tangent. That gives me, in the denominator, 1 plus alpha squared cosine to the 4th power of x. And because of the chain rule, on differentiating the argument of the inverse tangent, we have the squared cosine of x, which cancels out quite nicely. And we have the integral from 0 to pi by 2 of dx divided by 1 plus alpha squared cosine to the 4th power of x, and that's your derivative of I with respect to alpha. Okay, now what? Well, time to factorize the denominator. And how we're going to do that? Well, we'll make use of complex numbers. We could write this thing as 1 minus alpha squared I squared cosine to the 4th power of x. So that means we have the integral from 0 to pi by 2 of dx divided by 1 minus, on factorization, we have alpha I times cosine square x times 1 plus alpha I cosine square x. Okay, and now for a partial fraction decomposition, which in this case is pretty straightforward. We have integral 0 to pi by 2, and here we have 1 minus I alpha cosine x. We need a plus sign here. 1 plus I alpha cosine x. Ones here will do the trick, and to balance everything out, we need a factor of 1/2. So that's the derivative of I with respect to alpha, which means we need to evaluate two integrals now. We'll call the first one I sub 1, and this one I sub 2. Now for the integral I sub 1, we'll start off by expanding using the squared secant function. So I have secant square x up here and secant square x down here. That gives me the integral from 0 to pi by 2 of secant square x dx divided by secant square x minus I times alpha. And we can expand the squared secant in the denominator in terms of the squared tangent. So that gives me tangent square x plus 1 minus I times alpha. Now for a simple u substitution where we let u equal tangent x, and this means du equals secant square x dx. So I sub 1 in the u realm is the integral from, well, as x approaches 0, we have tangent 0, which is 0, and as x approaches pi by 2, the tangent function approaches positive infinity. So we have du divided by u squared plus 1 minus I times alpha, meaning that we have a very simple inverse tangent structure here. So this gives me on integration 1 by root 1 minus I times alpha, times the inverse tangent of u divided by root 1 minus I times alpha, with the limits being 0 and infinity. And this is really cool because this is the inverse tangent function from complex analysis that I completely butchered in my last video. I am terribly sorry about that. And I fixed the errors and re-uploaded the video. So it's cool now. If you watch it right now, it won't have those horrendous errors. Again, terribly sorry about that. So we need the inverse tangent function. In the wonderful complex realm, the inverse tangent of z is defined as 1 by 2I times principal log I minus z divided by I plus z. Okay, so over here we have z equal to u by root 1 minus alpha. So that means we have 1 by 2I times the logarithm of I minus u divided by root 1 minus I times alpha divided by I plus u divided by root 1 minus I times alpha. Okay, cool. And we're interested first in the limit as u tends to infinity of the entire thing. And to evaluate this limit, first let's expand using the reciprocal of u. So I have 1 by u up here and 1 by u here as well. This gives me the limit as u tends to infinity of 1 by 2I times principal log I divided by u minus 1 by root 1 minus I times alpha. And this is supposed to be divided by I plus I divided by u plus u, no wait, 1 divided by root 1 minus I times alpha. So in the limit as u tends to infinity, these two crash out to 0. We have negative something divided by positive something, which is, of course, negative 1. So we're left with 1 by 2I principal log negative 1. Now, negative 1 has the polar form e to the I pi. We all remember Euler's beautiful equation. So this implies that the limit as u tends to infinity of the inverse tangent of u divided by root 1 minus I times alpha equals 1 by 2I. The log and the exponential function are inverse functions. They cancel out. We're left with I times pi. Cancellation again. So this sorts out to pi by 2. And the 0 limit is pretty easy to work with. We have limit as u tends to 0 of inverse tangent u divided by root 1 minus alpha. That would be inverse tangent 0, which is, of course, 0. And this implies that the integral I sub 1 equals 1 by root 1 minus I times alpha, upper limit minus lower limit, giving us pi by 2. Now the integral I sub 2 is pretty much the exact same structure, but this time with a plus I times alpha. And that's the only difference if you follow the exact same algorithm. So that means we have pi by 2 times 1 by root 1 plus I alpha. And the target integral, that was the derivative of the target integral function, equaled 1/2 of I sub 1 plus I sub 2. So that means we could factor out pi by 2, meaning that we have pi by 4 here. No, wait, I'll keep one factor of 1/2 with these two terms. I have 1 by 2 times root 1 minus alpha plus 1 by 2 times root 1 plus I times alpha. Okay, so I have the derivative of the integral function now completely in terms of the parameter, meaning it's time to recover back the integral function by integrating with respect to alpha. So on the left, I have I of alpha, and here I have pi by 2 times a couple of integrals here that are pretty easy to evaluate. So I'm going to be left with root 1 minus I times alpha divided by I plus, negative sign because of the derivative being negative I. Okay, so I have 1 plus I times alpha divided by I. Okay, so I can factor out this I term. I have pi by 2I times root 1 plus I times alpha minus root 1 minus I times alpha plus a constant of integration c. And to determine the constant, recall that I of 0 is 0. So this implies that on plugging in alpha equal to 0, we have 0 equal to pi by 2I times root 1 minus root 1 being 0 plus c, which implies that the constant of integration is quite conveniently equal to 0. And we have I of alpha being pi by 2I times root 1 plus I times alpha minus root 1 minus I alpha. And the target case was alpha equal to 2. So that means the integral equals I of 2. And that would be pi by 2 times I times root 1 plus 2I, terribly sorry about that, minus root 1 minus 2I. And that's pretty much it, but wait, the answer should be a real number. So is this a real number or have I fucked up big time? Only polar forms of complex numbers will tell. So the plan is to convert these two square roots of complex numbers into polar form. So we'll start with 1 plus 2I, the absolute value of it being root 5, and the principal argument being the inverse tangent of 2. So this implies that 1 plus 2I equals, in the polar form, root 5 times e to the I times inverse tangent 2. And the square root, principal square root that is, would be root 5 times e to the I times inverse tangent 2 by 2. And by a similar token, we have the square root of 1 minus 2I being root 5 times e to the negative I times inverse tangent of 2 by 2. That means for the target integral I, we had pi by 2I times the difference of these two square roots. So that would be pi by 2I. We could factor out the root 5 term. And I'm going to need this 2I in the denominator. I'm going to absorb it here because we have a very useful structure in place. So it's e to the I times something minus e to the negative I times the exact same something divided by 2 times I. And this is how we write the sine function in complex analysis. In this case, we have the sine of inverse tangent 2 by 2. Okay, cool. So this implies that I equals pi times root 5 times the sine of half the inverse tangent of 2. And does this sine function have a closed form for this argument? Well, it does, and it's pretty cool. So let's call the inverse tangent of 2 equal to phi, which implies that the tangent of phi equals 2. In other words, the right triangle has a perpendicular length of 2 and a base length of 1, implying that the hypotenuse would be root 5. So that means we have the cosine of phi being 1 by root 5. And now that we have the cosine, we could invoke the double angle formula for the cosine function. We know that cosine phi equals 1 minus 2 times the squared sine of phi by 2. So this means that 2 times sine square phi by 2 equals 1 minus the cosine of phi, which in this case evaluates out to 1 by root 5. Which gives me root 5 minus 1 by root 5 on the right, which implies that the sine of phi by 2, phi being the inverse tangent of 2, sorts out to root 5 minus 1 divided by 2 times root 5. Lots of root 5s here. So finally, we have the target integral I being pi times root 5 times root 5 minus 1 divided by root 2 times root 5, and we're finally rid of it, and we're left with this cool looking form that can be made even cooler by expansion using the conjugate. So that would be root 5 plus 1, root 5 plus 1. In the numerator, what we're left with is in fact 5 minus 1, that's a 4. And we have 2 down here, root 5 plus 1, cancellation, meaning that we have 2 here. And root 5 plus 1 by 2 is the golden ratio. So all this means the target integral I evaluates to this beautiful result that is pi divided by root phi. A wonderful solution development for a wonderful integral. I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.